Thanks for the introduction. This talk is going to be about a private set intersection protocol that we developed, and it is joint work with Benny Pinkas, Thomas Schneider, and Gil Segev. So the problem of private set intersection basically says that you have two parties, Alice and Bob, who each hold a privacy-sensitive set of data. And what these two parties now want to compute is the intersection of their sets. But they want to do it in a way that they don't leak any information beyond what is in the actual intersection. And this is the way I show it here, it's really abstract. So let's get into some concrete examples. So the first example is the common contacts application. There, Alice is a mobile messenger app user, say WhatsApp. And she installed it on her mobile phone, and now she wants to find out which of her contacts also use WhatsApp so that she can chat with them. So what she holds here is an address book of users, of friends, and so on. Bob, on the other hand, is the service provider, so he's kind of the WhatsApp server. And he holds a database of users of the WhatsApp service. And now, obviously, Alice does not want to disclose her address book to Bob to compute the intersection, while Bob, on the other hand, does not want to reveal all of his users because thereby he would be compromising the privacy of his users. A second, a bit more complex example is the example of online advertisement. Here we have an online advertiser, in this case Alice, and we have somebody who wants to run an online advertisement, in this case Bob. What they want to do now is they want to measure the efficiency of an online advertisement. And in this concrete example, Alice has some users to which she's shown the advertisement. And Bob, on the other hand, has a lot of customers, or has customers, which actually bought the product he ran the advertisement for. Now, clearly, again, Alice, on the one side, does not want to disclose her set, because simply Bob could just take all the people to which the advertisement was sent, and he doesn't need to pay Alice for this. And Bob, on the other hand, does not want to disclose his information, because Alice could just take the data and run off and sell it to a competitor. Beyond these more practical applications, there have been some considered in research, and it's quite a problem that has been tackled a lot in research. So if you encounter the problem of private set intersection first, what you might come up with is the following solution. Here, Alice has some input elements X, Bob has some input elements Y. And what they do now is they simply hash the elements. And then Bob sends the hashes of his elements over to Alice, who simply compares them and checks whether there's an intersection. So clearly, this is extremely fast, as it just involves one hash function call per element on both sides, and Bob only needs to send his elements, or the hashes of his elements, over. Also, because we use a hash function, there's nothing Alice can really do, right? I mean, she can't, since it's a one-way function, she can't compute the hash back into the actual element. However, there are some problems, especially if the elements are chosen from a small input domain. So say, for instance, telephone numbers. These typically have a size of something like 32-bit, and it really doesn't take a lot of computing power to brute force 32-bit or to compute the hash of every element in the 32-bit domain. And even if the elements are sampled from a large space, Alice can still, at any later point in time, just simply check whether an element was in the set of Bob by computing the hash function of it, and then checking whether the hash was in the set of hashes sent by Bob. In order to counter this problem, several private set intersection protocols have been introduced throughout research. And what we did last year, or we had a paper also at USENIX Security last year, where we did a survey on the different technologies that these protocols were built on. So what you would typically use is either public key cryptography, generic secure computation techniques, or Oblivious Transfer. And just as an outline of this talk, I'm going to focus on semi-honest or passive adversaries, which means that these follow the protocol execution honest, but try to learn as many information as they can. but don't deviate from the protocol. There are private center intersection protocols for stronger malicious adversaries, but they are far from being practical. So the first class of protocols, the public key-based protocols, these have existed actually for some time. I think the earliest one was introduced around 86, which is 3 decades ago. And as the name suggests, they typically use public key crypto. So they just encrypt the element, send them over, and do some blinding, kind of. And 2 very good examples for these protocols are the Diffie-Hellman-based protocols by Katharina Meadows and the blind RSA protocol by De Cristofaro and Sudik. And both of these protocols just need around linear in n number of public key operations and messages sent, where n is the set size. Generic secure computation techniques are a bit of a different thing. So in generic secure computation, we can actually evaluate any function that we can represent as a Boolean circuit securely. That means that if you have a problem, if you have a function or something, just express it as a Boolean circuit, and then you can use standard techniques like Gauss-Gauss circuits or GMW to evaluate these functionalities securely. The current most efficient protocol or circuit description for the private set intersection functionality was given by Huang, Evans, and Katz and at NDSS 12, and requires around n sigma log n symmetric crypto operations, where sigma is the bit length of the elements. Finally, we have the class of Oblivious Transfer-based protocols. Oblivious Transfer is kind of one of the cryptographic primitives. It's a protocol where we have a sender and a receiver. The sender, Bob in this case, holds 2 strings, S0 and S1. The receiver holds a choice bit, and he wants to obliviously receive either of the 2 strings. That means that Bob is not supposed to learn which of the 2 strings Alice received. Also, Alice is not supposed to learn any information about the string that she didn't choose during the oblivious transfer. We nowadays have really efficient protocols which are based on OT extension protocols and so on to compute this oblivious transfer functionality. So this is actually really cheap. And this is the reason we've actually seen in recent times quite some protocols that are based on oblivious transfer sprung up, which are efficient, let's say it like this. Examples are the Bloom filter-based protocol by Dong, Chen, and Wen, or the protocol that we introduced last year at USENIX, which is based on oblivious transfer and hashing techniques. We implemented and evaluated these protocols last year and kind of compared their communication to their runtime. So what you see here is their communication in megabytes on the Y scale and their runtime in seconds on the X scale. And you have in red the public key crypto, in blue the generic secure computation, and in green the OT-based. Also note that both X's are in logarithmic scale. So for the public key-based primitives, they really have low communication. Since they only send a few ciphertext rounds per element, they're really quite communication efficient. However, they have a large runtime because they use 1 public key operation per element in a set, which takes a long time. The generic secure computation-based techniques both have a high runtime and high communication, which is simply due to the fact that they have to evaluate a Boolean circuit for them, which is comparably expensive. However, they have the huge advantage that you can easily extend the functionality. So if you want to compute something different, you just change your Boolean circuit, and you don't need to prove the security anymore. Finally, you have the oblivious transfer-based protocols, and these provide really a good trade-off between communication and runtime. However, if you look at the naive protocol that I've sketched out in the beginning, a protocol that in our case is used in practice very often, there's still a huge performance gap of over order of magnitude in both communication and runtime. So one might argue that the secure PSI protocols are still far from practice. And this brings me to our contributions. In this work, the overall goal is just to make private set intersection more efficient in terms of runtime and in terms of communication. And we do this by trying to, or through 3 different contributions. First off, we introduce a technique that we call phasing, which means permutation-based hashing, and which allows us to kind of create a generic technique for private set intersection protocols that compare elements. We then apply our technique to generic secure computation-based protocols in order to achieve better results for them. And finally, we improved the Oblivious Transfer-based protocol from our USENIX paper last year. Before I go into the details of our contribution, let me first briefly revisit the protocol from the OT-based protocol from last year. So I have a very concrete example here, which hopefully makes it easy. The core of the protocol is that you want to securely compare 2 elements x and y. So Alice has an element x, Bob has an element y, both are of 3-bit length, and now they want to know whether these elements are equal without actually revealing the elements. So what they do is Bob samples 2 lambda-bit strings, where lambda is the statistical security parameter, so say 40-bit. And then they run the Oblivious Transfer, where Alice inputs the least significant bit of her x value. Then Alice obtains the 0 mask, or the 0 random string. They do this for the 2nd bit, and they do it for the 3rd bit. And Alice receives the mask that corresponds to her input x on that particular position. What Bob then does is he takes the masks from the Oblivious Transfer and just uses the mask that correspond to the bits of his input y. So he takes the green 0 mask, the blue 1 mask, and the orange 1 mask, XORs them, and sends them to Alice. All that Alice needs to do now is simply XOR her own mask and compare these 2 random masks, or compare her random mask with the mask she got from Bob. Now, if one wants to extend this to set intersection from the basic equality test, then what one needs to do first is the set inclusion functionality, which we did also last year. So what we basically do is we efficiently extend it to compare multiple elements. And finally, if one wants to have this private set intersection functionality, one can simply run the set inclusion protocol on each input element of Alice. However, as one can see, there's a huge overhead incurred because suddenly you need n² comparisons where n is the set size. In order to reduce the number of comparisons here, we use the hashing to bin techniques. And I'm again only going to give a short example here. So say Alice has 3 input elements and Bob also has 3 input elements. What they do now is they construct, or Alice constructs, a so-called hash table, which just is a lot of bins in this case. Then Alice computes the hash of her first input element and maps the first input element to the bin that is identified by the hash of this element. She does this for the 2nd element, and she does this for the 3rd element. Bob, on his side, does the same with the same hash function, and then they can simply compare the elements that were mapped to the same bin. Now clearly, if they input the same element, then the hash must have been equal. That means that the element was mapped to the same bin, and if they compare the elements in the bin, then the comparison succeeds, or finds the intersection. The overall number of bins is on the order of n, while on Alice's side, the number of elements in one bin is approximately 1 because we use a technique that is called cuckoo hashing. And on Bob's side, the number of elements that are in a bin is around log n over log n. So this reduces the number of comparisons that one has to do from n² to n log n over log n. This brings me to our first contribution, the permutation-based hashing technique. So in basic Oblivious Transfer-based protocol, what we did was to compare the elements, or where we compared the elements x and y. We did the comparison bitwise, so we compared each bit of the element. But this also means that if we have shorter elements, we will have more efficiency, because we need to compare less positions. So what one might first think is that we can simply take the elements, hash them, and use a shorter representation. However, due to collisions and due to the birthday paradox, we actually need to make the output hash quite long, which is around the order of 2 times log n plus 40 bits, which is often longer than the actual input elements. What we did instead was to use a permutation and thereby use the permutation to map the elements into one specific bin and then store a shorter representation of the element in that bin. I will again just give a brief example of how this works. So you have an element x, you split it into 2 halves, a left half xl and a right half xr, where the left half xl is around log n bits. You then define a pseudorandom function f, which maps from the right half to the left half, as well as a permutation p, which given x, XORs the left half onto the PRF output of the right half. And what you simply do then is you store the element x in the bin that is indicated by the permutation, and you don't store x, you store the right half of x. And this reduces the bits or the representation length of the element that is in the bin by around log n bits, which means that you have less complexity for the comparison, as well as a really nice feature, which is the larger sets grow, the more elements you're processing, the more cheap it will get doing these equality tests, because you compare less bits. For the second contribution, the circuit-based private set intersection, we actually went ahead and applied this phasing or permutation-based hashing technique to circuits. That is, we again map the elements to bins and then use an equality circuit to compare the elements in these bins. And what this circuit does is simply take each bit and test it for equality, which is a standard functionality. The advantages that we have from here is that the number of communication rounds for some protocols, such as GMW, is independent of the set size. It only depends on the number of bits. And also, since we only build really, really small circuits, but build a lot of them, we can use so-called single evaluation multiple data techniques, which Niklas will talk about in the next talk. However, there's a small problem here, namely that we leak information if one of the parties knows the actual number of elements in a bin. So say Bob knows that Alice hasn't mapped one element to a particular bin, so he can say that one element didn't correspond or wasn't in her input set. And on Bob's side, the same. So what we need to do is we need to pad the bins to a certain number of elements. In Alice's case, we pad them to 1, while in Bob's case, we pad them to log n over log n. So overall, we need around n log n over log n comparison circuits, which each have around sigma minus log n bits, where we need for each sigma minus log n symmetric crypto and communication. In total, this gives us a rather large formula, which I'm not going to read out. And to compare the sort compare shuffle circuit from Huang, Evans, and Katz is around the same order. So in order to actually find how much concretely we gained, we did experiments on it. So in blue now, you see the evaluation using the sort compare shuffle circuit. On the left side, you see the GMW technique, and on the right side, the Yao's couple circuits technique. These are basically just two ways of how to securely evaluate a Boolean circuit. In this case, both x's are not logarithmic scale anymore. So what we did now was to implement and evaluate our protocols, and we found that both decreased the runtime around 1.5 or by factor 3, and the communication by factor 2. I'm now going to come to the last contribution, the OT-based private set intersection protocols. Briefly, what we did here, because I don't want to go into the details, is that we applied the permutation-based hashing and did 2 or 3 optimizations, such as using more hash functions in the hashing scheme, as well as changing the underlying protocol in order to reduce the work set of the client, which helps especially for larger sets. We also benchmarked the protocols against each other, and what you see here is the results for varying number of elements, from 256 to 16 million, and in blue are old protocol, in green our new protocol, and with different bit lengths ranging from 32 to 128. What we can see here very nicely is that our new protocol scales much better with increasing set sizes, simply because of the permutation-based hashing technique. And due to our protocol modifications, it also allows allows processing larger sets. So we were able to evaluate up to 60 million elements, even for 128 bit elements. What this kind of gives us as a whole is, this is the first kind of snippet from the first picture I've shown you. And we were able to decrease the runtime by around factor 20 and the communication by factor 4. And compared to the naive protocol, we are only 3 times slower and need around 8 times more communication. So to conclude, we've introduced more efficient PSI protocols that reduce the overhead for runtime as well as for communication. And right now, we're only 3 times slower than the basic naive protocol. In order to do that, we use the permutation-based hashing technique in order to reduce the bit length of the elements. Also, we introduce a protocol for generic secure computation-based PSI where we designed a new circuit. And finally, our code is online at GitHub. You can check out the web address or just enter private set intersection in GitHub, which is most likely easier. So thanks for your attention, and I'm happy to take your questions.
Hi, thanks for the nice talk. So this is kind of a generic set intersection question. So when you say little n, you're assuming that the number of records in both parties is roughly the same. Is that an assumption that you typically make?
We have 2 different sets, or 2 different experimental settings. For the one setting, for the numbers I've shown you, the set sizes are equal. I forgot to mention that, by the way. And we have experiments in the paper where one party has very few elements, say only a few thousand, while the other party has several million elements. And we show how these protocols compare in this setting. But I didn't show you the numbers of that here.
So that's very interesting, where when one party has many less elements than the other. So in that case, is there an inherent, I saw that every communication cost in every protocol was n times something. Is that an inherent lower bound, even in that case, when you have many fewer elements on one of the parties?
Yes, it is. Or let me rephrase it this way. I think it's really low bound that you have to do communication that is linear in both of the set sizes of the parties. So if you have 2 parties, one has very few elements, the other has million elements. You need to transfer data for each one in the million set or you need to do communication that is linear in the bigger set size. I don't see a way of getting around that, and that's a limitation that really all the protocols that we've analyzed up to now have.
There's no one behind me, so I'll just, do I have time for a little bit more? Oh, you also have a question? Okay, well, okay. Yeah, so in the case when one party has many fewer elements, so I imagine you could get away with lower than little n communication using something like FHE. So one party sends his data, the other party uses public key FHE and scans the entire database and sends it back. Is there a disadvantage in doing that, aside from the fact that it's FHE?
I don't really see a disadvantage at this point. It depends on the FHE scheme. I would need to see it actually, because I'm not sure well, you need to compare it. So one party, the one with the smaller set size, encrypts this element, sends it over to the party with the bigger set. And he does some computation on it.
Correct.
But I'm not entirely convinced that the party with the bigger set can actually send the small set back. I'm not sure whether it's necessary to send a lot more data back. So
No, I don't think that it is. You should be able to send a small amount of data back under any reasonable FHE scheme. I'll let Elaine take the podium. Thank you.
yeah, thanks for the questions.
I also have a question and a comment. Like, you have a specific construction of the permutation-based hash. And does the choice of the hash function here have significance on your performance? And if so, can you elaborate on the motivation for this specific choice of hash function?
So I'm just going to repeat the question to see whether I got it correctly. You were asking about the instantiation of our permutation-based hashing technique, which we used. So basically, the P on this side. Did I get it correctly?
Yes. Like, what kind of properties do you want the hash to satisfy? Like, can you state like what generic hash function you need here, and why your specific choice of hash function here improves your performance?
So there's not a big of a performance issue here. The performance doesn't drop that significantly. The properties we need of it are basically uniformity, I think, and or our uniformity. We don't even need one-wayness. So the way we instantiate it is by a table lookup. We generate random data, and then we do a table lookup in order to obtain the random data for it.
And the hash function doesn't go into your OT circuit, the circuit.
No, it's not. It's just a simple hash function. It doesn't need to be any generic secure computation construction. It's only a plain text hash function.
Okay. I also have a comment. I think so. Basically, there's this secure genomic computation contest earlier this year that was hosted by iDash, and they also had a task in which the contestants like built secure computation protocols for doing this set intersection. And I think some of these results are quite interesting. People use like gobble circuit-based approaches, and I think some approaches also like use hash functions to basically compress these large numbers into smaller representations. And also, there was also an FHE-based solution, like I think IBM's solution, for instance, they use FHE and then they represented sets using these polynomial representations, and over like a data set of 100K or 200K, I think it took like about 5 minutes for this to run over like a wide area network. I think the gobble circuit-based solutions maybe took a little less than that, maybe on the order of minutes too. So you might want to look at that too.
Yeah, that is true. We were planning to look into that, actually.
Okay, great. Any other questions? Okay, let's thank the speaker again.